So the idea is that this shell method that we learned on Wednesday is an alternate for volumes of revolution. Okay, so it's whenever you have a disc or washer situation, that's a time you could potentially do a shell method. Okay, that's where it's an alternate. As far as these solids on a base, you know, that is your only option right there is the slicing. It wouldn't ask any, it wouldn't ask it any other way, so it wouldn't be confusing. So if I were to ask you, I said do the shell method or something, you know, it would be on one that was set up to do that. It would be a revolving one. Okay, because again, it's a circular thing. It's often called the method of cylindrical shells, right? It's because that's what it creates when you go around, when you wrap around, when you take, you know, your strip. Here's your axis of revolution. Here's your strip, and you create this cylinder-shaped, right? This layer, or in like it's typically called a shell. So, and then you just got to know the formula, and then again, this H is easy. That's what we always do, the length of the strip, what top minus bottom, right minus left. And the strip is always in the region. That's another thing that's important to understand. Big R and little r, remember, always go from the center. So sometimes those go through the region and they're outside of the region, you know, in the empty space as well. But H, whenever you're revolving that region. So your shell is in the region, so that strip is always in the shaded region. And then P is just the distance from the center to the strip, and we said that always looks like X minus 5 or 3 minus Y, or it always looks like that. Okay? All right, so what was number 4? You're supposed to revolve around what? What were you revolving around at number 4? X-axis. Okay? So which way is this strip going to lay? Let's just do shell method on these first ones here, because that's what you're supposed to do. So that's going to be horizontal, right? It's always parallel to the axis of revolution. Okay? Always parallel to. And so we label, so if we're going to do a shell method, how do we label this strip right here? How do we label a horizontal strip? With a Y, right? With a Y. Okay? Now, to write, because this is a part I just want to make sure we can practice and know. So to write H is going to be what? Right, which is 4, minus left, and I don't, what is that equation? Y equals negative X plus 2, or 2 minus X, I think. 2 minus X is right here. So make sure you write it, you know, put it in parentheses. But, oh, that's not right. It's got to solve, we got to solve that for X, don't we? So that'd be negative Y plus 2, so it'd be 2 minus Y, right? There we go. All right, it's got to be a Y. So it's got to be right minus left. That's H, that's what we're used to doing. What would P be, though? What would you put for P? Top minus bottom, right? Now, it makes sense, because remember, we want the ball, and you're going to know this because your answer will come out negative, and then just be like, oh, okay, it should have been positive, so that's really the only issue that what happens. But it's got to be top minus bottom, right? It's got to be the distance from the center to the strip. So, okay, Harry, there's no way you could say your clock says 8:03.
He wants to.
Okay, 0. You got to go top minus bottom from the center. Remember, from the center. So you can literally draw another strip. I mean, you know, if that's helpful, right? I often will do that. I'll draw from the center down to the strip, and then just say that's 0 minus Y. So think of it as a top minus bottom. So 0 minus Y is what you want to have there, and it makes sense because Y is down here. Y is negative, right? Y, this strip, is at a negative Y location. So if I just put in Y minus 0 here, that's going to be a negative value. P is going to be negative. We don't want that. We want H to be a positive number. We want P to be a positive number. And so that's why it's got to be 0 minus Y. Okay? And so then your integral will just be 2 pi, and then it'd be H, and then times P. And then the strips go from what? Down here, -2, up to 0. right? Okay. This one, we're revolving around here. What direction do the strips have to go? Vertical, right? Got to be parallel to the axis of revolution. Have to be parallel to the axis of revolution. So vertical strips are usually nicer. So this would be a problem that's probably a little nicer. Matter of fact, it's a lot nicer to do shell. Almost the only way to do this, because how are you going to solve this for x? Right? If we wanted to do a washer method, there's empty space here. If we wanted to do a slicing method, we would have to draw big R and little r right here. And on this equation, the 4x minus x squared, this upside down parabola right here, okay, when we go to subtract that, we'd have to have x equals here. You cannot solve that for x. You can factor out an x, but you're going to have 4 minus x. You can't get the x by itself. Okay, so really a washer method, that's why I never gave you one like this when we first learned disk and washer stuff, because you wouldn't be able to solve that for x. So here it's a huge advantage to be able to write this with a horizontal or with a vertical strip. Okay, because now we can go 4x minus x squared, the top curve minus the bottom curve, and then p, what do we label this strip? We label that strip as x, so the distance from the center to the strip, right minus left, x minus 0, which is good because x is positive in this case. So x minus 0. So p would be x minus 0. Okay? So the integral would be h times p, and the strips fill the space from 0 to, what is that up there, 2? And then don't forget the 2 pi on the front. Okay? All right. Revolving around the x-axis. Now, here, and I did 12 say you're supposed to do shell method, right? So this one is not a fun one to do with shell method because you got to do what? You got to split it up into 2 because since your axis of revolution is here, you need horizontal strips. And so horizontal strips would have to split right here at 1/2. I think that's at 1/2 right there. So you would need an integral that goes 0 to 1/2, and you would need an integral that goes 1/2 to 1, I believe is where that happens. Okay, what was this equation here? 1 over x? Y equals 1 over x. So x would equal 1 over y. Okay, so this strip down here, so the bottom strip, h is going to be 2 minus 1. And what's p going to be on this one? We label that y, it's just going to be y minus 0, right? What's h on this top one? One over y minus 1, right? So this is going to be h, which is 1, times y dy with a pi out in front. Oh no, that's the top one. No, I got these backwards though. I got these backwards. Now I know. Okay, so here's the bottom one, 0 to 1/2, and then this one, there's your h, and then what's p on this one? What's p on 12? Also y minus 0, right? I mean, the strips are y. I mean, this strip's y, just happens to be somewhere between 1/2 and 1, and the strip below happens to be is somewhere between 0 and 1/2, but it's still y. So the distance from the strip to the center is still y minus 0 on both of them, right? 2 different strips, but the same name. And so this would be 1 over y minus 1 times y with a pi, 2 pi. Okay? So we would not choose if this was a quiz and you were given this region to revolve around the x-axis, and I said, find the volume, you would do just a regular radius one, right? Just a circle. This would just be a solid slice, and you would just do that, right? It'd be much easier. Pi radius would be 1 over x minus 0, so 1 over x squared dx from 1 to 2, right? That would be the way to do that. All right. 17, now we're revolving around over here, so you're going to want a vertical strip like so. If we name that x, so h is what? What is this? It's just square root of x again? square root of x, so this would be square root of x minus 0, p 6 minus x, 6 minus x. The distance from the center to the strip, 6 minus x. Okay, and once you got that, you got it, and the strip fills the space from 0 to 4. Okay, and run through this real quick. What method are you going to choose for this one? You do either. It said use whichever. What do you think? Probably, I mean, to be honest, I would do the one that would give me the vertical strip every time, right? If I can get a vertical strip every time, I'm probably doing that one. So that would just be a disc, right? Just a solid circle strip. Okay, it wouldn't be hard though. It wouldn't be hard. I solved it for x. It wouldn't be hard to do a shell. Here would be the blue would be your shell method. It wouldn't be hard. Any of these you want to see, A, B, C, D? Let me just read you the answers real quick if you don't have those already. So on 21A, it's 128 pi over 7. On 21B, it's 64 pi over 5. On C, it's 96 pi over 5. And on D, it's 320 pi over 7. Okay? Any of those, don't be shy. Let's look at them. We'll probably review one day next week. Probably Wednesday or a little bit. Probably quiz, or Tuesday. I think probably quiz Wednesday, you were saying. Any of those, A, B, C, or D, you want to see? Okay, B is probably going to be a shell. You're going this way, so if you want a vertical strip, you're probably going to do a shell like that. Okay, here, probably going to do a shell on part C if you want to do a vertical strip. Okay. P, what would P be in this one? What's P in part C? 4 minus x. Okay, good. Easy. And then this one, you're probably, if you want to do a shell, you'd be that way, so you're probably not going to do a shell. You're probably going to do a washer. So what are you going to have? You're going to have big R here, and you're going to have little r right there. Oops. All the way down to there. So you have big R, you're going to have little r. Right? Like that. Okay? All right. So let's get your notes out. Let's get through the thing we were going to work on here today. Like I said, we got two last things to cover in chapter 7. How many people took physics? In physics now. Did you do work? Good, that was wondering. Not really. No, didn't do much. Okay. But you did do this concept. You talked about the concept of work. Okay. Well, is it?
It's man. It was playing.
No comment. All right. So it's much like many, and I think I've mentioned this before, where you have, like a high school physics class is more algebra based, right? In other words, it's constant forces, constant acceleration, the equations that you use. So when we talk about position, velocity, acceleration, those connections back to physics and motion, a lot of that stuff, a lot of those equations fit for that. And then if you move on in that area, in an engineering realm or the physics around that kind of thing, then in college you would take a calculus-based physics. And then you work with variable forces and you work with variable acceleration. And we work with variable acceleration, that just means we have an acceleration equation, right? Like in physics, you work a lot with gravity, free fall, right? Where accelerations are constant, negative 9.8. But we've had many situations where we just give you an acceleration function, right? What that means, it's a variable acceleration. It's got different accelerations at different times, right? And so we use calculus to figure out distance traveled and so forth based on that. And work is the same thing. So in physics class, you would have maybe done a problem like this, where, okay, and so the idea of work, so if you haven't been in physics, so work, the equation for work is force times distance. Now the units, I think, is joules. I think is, if you're in the metric system, which is Newton meters. Newtons times meters. Newtons is a unit of force, and then distance, so Newton meters. Now, our book, the math books are usually in English units, so you're going to see a lot of these be foot pounds, right? Foot pounds will be the units, okay? Distance measured in feet and the force measured in pounds, okay? So so work is a force applied through a distance. So the idea being that if I took this thing, okay, and I lifted it, and I stood here and I held this, I'm not doing any work, right? Now, you know, I'm by the physics definition, right? Now it's taking some, you know, it's taking something to stand here and hold this up. I mean, if I took 100-pound weight and stood here and held it over my head like this and just stood here, you know, you pretty soon your arms start shaking. I probably couldn't even lift it, but whatever. But you're not doing work. It has to be through a distance. Now, the act of lifting it. So, if you took a 10-pound book, lifted it 7 feet off the ground, 7 times 10, that's 70 foot-pounds of work is what you've done. Now, technically, that's not accurate. Why not? Here's why. Because the book does not weigh the same. If I pick up a book that's on the floor that weighs 10 pounds, it doesn't weigh the same on the floor as it does when I get it 7 feet over my head. Why not? Because weight is a measure of gravity, right? And the farther you get from the center of the earth, the less gravity there is, right? And the less things weigh. Now, it's microscopic difference, and so we'd have to go into a lot of decimal places to tell the difference. So it's, you know, and many times you get problems like that. Like, for example, the classic one is, you know, we did a one about the baseball pitcher, right? We said, you know, and we talked about the horizontal velocity. Remember, the ball was actually traveling faster when it got to the plate than when it left his hand, right? Because we were ignoring what? Air resistance, right? We said, let's ignore it. Well, that's kind of a big one. You can't really ignore air resistance. But a lot of times you do those problems in physics, you know, well, ignoring air resistance or wind resistance or whatever, friction, you know, and that's kind of a big one to ignore, right? This would not be a big one to ignore, right? So you got a 10-pound book on the floor, you pick it up, you lift up 7 feet, it essentially still weighs 10 pounds, right? So that's fine to ignore. And we would ignore that. We're probably not going to pay attention to that. But another one that we're going to do where we're going to change. So that would be, technically, that'd be a variable force, because as you're lifting it, the force is changing. The force is changing, not a constant force. Okay, now we're going to do another one where we pull where we talked about pulling a rope and a bucket, you know, pulling a bucket full of water out of the well, right? And we pull that up. 70, say it's a 10-pound bucket, and you go 70 feet. That'd be 700 foot-pounds. But technically, as you pull it up, you've got less rope, right? With every pull, you know, you've got less rope, because now you got rope just laying on the ground. So you're pulling this up. So you're actually lifting the bucket and the water and the rope. But with every pull, you know, you're actually lifting less and less rope, because some of the rope's just kind of laying on the ground here as you pull it up. Now, in physics class, you'd say, well, we'll ignore the weight of the rope. Well, that's a little more problematic, because that probably does have some weight to it. Or another one we'll do is there's water leaking out of the bucket. So as you pull it up, the water's leaking out. So the pounds are changing. So that requires calculus, right? So these changing quantities, that then our physics formulas don't apply. Okay? So we're just gonna just barely scratch the surface with this concept, okay? It's more of a Calc 2 thing. You notice you haven't seen any of this in the packets, but that's okay. It's one of those things we're gonna kind of touch on that gets into Calc 2. Okay, so here's one more thing from physics we need. Hooke's law. one of the examples we're going to do is stretching a spring, stretching or compressing a spring. Now, you can think of like a slinky kind of a thing, or you can think of something a little more solid. But stretching or compressing a spring uses Hooke's law. F is the force, so this is force right here on this side. Okay, and this is some constant, K, and then X is a distance. Okay, so this will be in feet. So if you had a spring that had a natural length of 3 feet, now we're gonna think of just stretching or compressing from one end of the spring. So let's say we had a big solid spring attached to the wall here, and it was sticking out 3 feet. So at rest, it was 3 feet. Now for us, stretching or compressing are gonna be the same thing. We're not gonna, one's not negative, that we're not gonna, it doesn't matter. The amount of force required to stretch or compress is gonna be the same either direction, okay? Just to keep things simple. So if we take this spring that's sticking out from the wall 3 feet, and we stretch it 5 feet, okay, for this particular spring, we're going to say that takes 10 pounds of force. So you'll be given that information, right? And then we can find K. Now that's called the spring constant. So each spring would have a different spring constant, right? A more heavy spring would take maybe 20 pounds of force to go that far, whatever, right? So depending on the spring. So you'd be given some information. So we would simply say, okay, 10 pounds of force would go in for F, and what would go in for X? What would go in for X? 2, right? So you got a natural length of 3. We stretch it out to 5. So you got to read it carefully. It says stretching it to 5 feet. If it would have said stretching it 5 feet, that's different, right? That would have been stretching it out to 8 feet. Okay? So you got to read it. The X value here is how far you stretch or compress. Okay? So from its natural length. So we stretched or compressed it 2 feet. And so K would be 5. And that would be called the spring constant for that particular one. Now you might get a real easy problem where they just tell you the spring constant. You know, for a given spring, the spring constant is 2.5 or whatever. They've just given you the K value right there. Okay, that's the spring constant. Okay, so these are pretty straightforward, simple problems. So the work required, guess what? It's an integral. Okay, so you can go ahead and write that down. We'll just talk about why that is. As we stretch that spring, right? So when I first stretch that spring, think about slices of the lemon. Let's say I stretch that spring. So what happens? Just imagine that. So you got this spring at rest, 3 feet long, and you start stretching. What happens? As far as the effort it requires to stretch it, it gets harder and harder and harder, right? The farther out you get, right? At some point, maybe you can't even move. Same thing with compressing, right? And so at the beginning, it doesn't require as much force. But the farther you go, the more force it requires. Variable force. Okay? So let's just say you take the first 6 inches. And maybe you just average the amount of force that it takes, right? Because it's changing even in those 6 inches. Now remember how we did that with the lemon slices? Remember how the top and the bottom worked right the same? They're more like peanut butter cups. So we had to kind of average the radius to kind of make it a cylinder. That's kind of what we'd be doing. And then you go another 6 inches in the front, and then another 6 inches. So you would take 6 inches, you take that little bit of distance times the force required, then the little bit of distance, the force required, then the little bit of distance, force required, little bit of distance times the force required. You'd be doing force times distance, and you'd add those up to get the total work done, right? You'd add up the force times distance. Well, what's the part of that you would want to, what would you do to get more accurate with that? Instead of 6 inches, you do 3 inches, and then or 1 inch, or ½ an inch, right? Well, that would go towards 0. What's the part that's going towards 0? The part that's disappearing, that's the dx part, right? That's the distance. So what do you got here? You got your force equation, which is Hooke's law, times, and then the dx is your distance. So so again, it's just, and again, I like doing this because it just reinforces what we've been talking about with what the integral is. Oops, that's not working. Force times distance, right? The dx is the distance. And so this gives you, this is pounds, and this is feet, and so that gives you foot pounds for your unit. Just like area inside of the integral gives us volume, because it's area times the thickness. That gives us volume. Okay, so for a spring problem, it's very simple. All we need is this force equation we get from Hooke's law. We stick that inside the integral, and away we go. Now, for the integral, now the question is, what about the a and the b? So for the problem we just did back here, k would be 5. So inside here we would put 5x dx, and then our integral would go from what to what, do you suppose? Now remember, these numbers have to be x's, so they have to match the units what x's was and dx was feet. So what do you think?
3 to 5.
Almost always everybody says 3 to 5. So you're in good company, but it's not right. What do you think? It's 0 to 2. So at its natural length of 3, we call that 0, because we've stretched it 0 at that point. So at its natural length, there's been no stretch or compression, so that is 0. So if we go from 3 to 5, what we've done is a 0 stretch to a 2 stretch. So it's 0 to 2. 0 to 2. Okay? Now, it's possible that they may give you a problem or say, okay, the natural length is 3, and they might say stretching it from 4 feet to 5 feet takes this amount of work, or something like that, right? And now all of a sudden, your integral might be from 1 to 2. How much work is done stretching it from 4 feet to 5 feet, right? That'd be from 1 to 2 then. 1 to 2. Okay, the natural length is 0. That's important. Okay, so anyway, in that case, you just do that, and your answer's in foot-pounds, and you got it. So spring is a pretty easy one. Okay, let's talk about the rope and the bucket then now. Okay, rope and the bucket. So we've got down at the bottom of our well here, we're going to call that 0. And we're going to raise it how far? 20 feet? Okay, so up here is going to be 20 feet. Okay, so 0 to 20, that'd be like our Y, right? Since we're up and down. So a 5-pound bucket with 2 gallons of water is raised 20 feet. The 20 feet of rope weigh 1.6 pounds. Now sometimes they'll give you how much the rope weighs per foot. So some problems will say it's 1.5, or it might be 0.25 pounds per foot or something like that. Here, the 20 feet of rope is 1.6 pounds. So now why is that important? Well, you're going to see here in a minute. Okay? So how much work is done in raising the bucket? So now we've got 2 things of work we want to add up. 2 things of, well, actually a force that we want to add up. Okay? So we want to have the bucket, that's the easier part, so let's do that, plus the rope. Okay? And then our dx part is going to be our feet. Okay? So we want this to be pounds. So very much like this equation was, we want an equation for pounds in here, and the dx will be our feet. So again, same thing with our variable force. If we raise it up 6 inches, we have so much rope out plus the bucket. But then the next 6 inches, we'll have 6 inches less rope out that we're lifting, right? So we're not lifting quite as much. And there's 6 inches, and there's 6 inches, and again, we would let that go down to nothing. Well, in this case, we might want to call that dy, but that's fine. We'll call it the instead of that. Okay? All right. So how do we get the pounds of force that we're lifting? Well, the bucket's easy. 5-pound bucket with 2 gallons of water is raised 20 feet. So how much is the bucket? Well, it's 5 pounds. So that's easy. That goes in there. But now we got it. Well, I probably should put plus water here. Sometimes a problem gives you the bucket and water together. Okay. Sometimes they're separate, but here they gave it to you separate. So we have a 5-pound bucket, 2 gallons of water. Okay, we need a number here. We need a number that would be given to you. It's in your book. Let me look it up here real quick. I would give you this number in the problem. It's 62.5, I believe, but I think sometimes the book uses 62.4. It's the density of water. Double check here. Must be a nerve problem, so that's okay. So 2 gallons of water, so this weighs 62.5 pounds per, that's not gallons. That doesn't sound right. What's that? Where? It must be in the, it must be in the homework. Oh, yeah, oh, gosh. Okay. Why do I not have this number on here? James, use that Chromebook for something useful here. How many cubic feet a gallon? Yeah, this gallon weighs what? There you go. All right. So I would give you any of these conversions that you need, and I don't know why I don't have that on it. So 2 gallons of water, but the idea we're trying to get across is we need to have in our formula, in our integral, the bottom line is for work, we need pounds and then feet to show up, right? Now in our 2 examples that you're going to be responsible for on the quiz, it's going to be pounds and feet, pounds in here. Okay, there's another example that I might talk to you about, but it's not going to be on the quiz, so it depends. If we have some time, I might show you this example, but not require you to know it on the quiz. So the ones we have to know, we have to do force here or pounds. So we need to get pounds. Everything's got to be in pounds here. So 5 pounds, and then what'd you say it was? 2 times 3, 4. Okay, so 1 gallon is 8.34 pounds. So 2 times 8.34 is 16.68, we'll say. So that's how much, and that's not going to change, right? Other than, again, we're going to ignore the whole gravity thing, right? As we lift it up, we're getting farther from the center of the earth. That part we are literally going to ignore, okay? So those are not going to change right there. Okay, but the rope is changing. So this is the part we have to work on. Of all the work problems, this is probably the part that we have the most difficulty with, is getting the equation of the rope, because it's going to change. So it's going to have an X in it. Okay, now X is our distance from 0 up to 20. Okay, so what would be an equation? And the rope weighs 1.6 pounds for 20 feet of rope. Ideas for how to write this. A couple different ways you can do it. Okay? How much is the rope going to weigh down here? When we first start pulling, right? How much is it going to weigh when we're up here? 0, right? What do you think? If we let Y be the weight of the rope, if we let Y be the pounds, what do you think? 1.6 divided by 20 be your pounds per foot, right? Okay, 1.6 divided by 20 is pounds per foot times X. Right, it's going to be, because when X is 0, right, when you haven't lifted at all, you want to get an answer of 1.6, right? So when X is 0, this would give us 1.6. When X is 20, we want to get 0. So what am I missing? Negative on that. Okay? So one option is to just build that equation, right? So if it's halfway, at 10 feet, it should be 0.8, right? 0.8. Well, you put a 10 in here, sure enough. 10, cancel that, that'd be negative 0.8 plus 1.6, that'd be 0.8. That would be, so at any X value, now again, it's up and down. These are our X values. It's up and down, it's kind of backwards. But using X as our distance, this would give us our weight of the rope that we have, our pounds. Okay, now, if that, so basically this is your pounds per foot. So if the problem would have just given it to you in pounds per foot, that's like your slope, right? That's like your rate of change. So that goes in front of here. So it's really just a linear equation with the y-intercept being the total weight of the rope and this being the pounds per foot as the rate. That's really all it is. Okay, it works that way every time. Okay, now what, I've had some success, people that had trouble just coming up with that on their own. So anyway, that would go in here. Okay, so it might be good to make this, what would it be, 0.08, all right, x plus 1.6, right, as the equation. Okay, and we'll get to, well, what's the integral going to go from what to what? 0 to 20, because that has to match your feet, and we're going to add up all this work from 0 to 20. Okay, so that would be your work. But here's what I've had some luck with people doing. This is your feet, this is your feet, this is pounds. So say, well, when there's 0 feet of rope pulled up, now that's pulled up now, right? At the beginning down here, when there's 0 feet of rope that's been pulled up, you have 1.6 pounds of weight. When there's 20 feet of rope pulled up, you want 0. And then just do it like a linear equation, right? Just do a slope calculation, so 0 minus 1.6 over 20 minus 0, right, which is your negative 0.08. And then just put it into a y equals negative 0.08. Well, here's a y-intercept right here. So you really don't, but you could go x minus 0 plus 1.6. So some people have felt better about doing that. Just saying, okay, there's 0 feet of rope pulled up, it weighs 1.6. At 20 feet, I want it to weigh 0, right? And that kind of thing. And that especially can work good, like in the leaky bucket, if you've only got half the bucket filled, you know, so what's the weight? It doesn't always go to 0 at the end, you know, so that's not a bad way to do it. You can get a couple of points in there, because it's always going to be linear. The ones we do here are always going to be linear as they're changing. And so you can just do a slope, get 2 points, get a slope, and then do a line equation with the point, the slope, and then that's what goes in there. Okay, so this is constant. The bucket doesn't change, the water doesn't change, and then you got the rope. Okay, last thing real quick then. Yeah, we're not going to do that. Okay, so what happens if the bucket is leaking and it's going to be empty when it gets to the top? Okay, it's going to be empty when it gets to the top. Well, this time you're going to have the 5-gallon or the 5-pound bucket. Okay, we're going to have the same rope, so negative 0.08x plus 1.6, so you'll go through that same business getting the rope. And now what about the water? Well, again, I think it's good to make yourself I mean, if you can just figure it out yourself, that's fine, like we were talking it through. But when there's 0 feet of rope pulled up, how much did the water weigh? 16.68. When there's 20 feet of rope pulled up, 0. So again, do a slope calculation, 16.68 minus 0, and then 0 minus 20, right? Yeah, that's your slope. So 16.68 over 20, so that would be, what, 8.34, so 0.834. So y equals 0.834, and then x minus 0 plus 16.68. Right? So we'd have 0.834, x, that's negative. Yep, negative, that slope's negative. Plus 16.68. Okay? dx, and again from 0 to 20. So, constant, the bucket doesn't change weight, but the rope is changing weight and the water is changing. The amount of water weight is changing as you go up. But they're both going to be linear, so not too bad. Okay? So, that's what we're going to do. Let's look at, on your homework, Dan, on your homework sheet, it's going to be the 7.3. Don't forget, you were gone. We had that 2015 that we hopefully got a lot of work done on. That one will probably be due earlier than the sample 4, just because sample 4 is bigger. Okay, we'll have some work time on sample 4. We'll be talking about it next week. At some point, one of the days we may talk about 2015 a little bit, but if you weren't here and so forth, you might have some work to do over the weekend. When you're blizzarded in your house, you can't go anywhere, that'll be a good thing to work on. When's what?
Girls Pack next week.
Friday.
Will you be here that day?
I will not be here that day.
wanted, I was hoping to find out the call
Let's go. What day are you not gonna
Thursday.
All right, so 7.3 line, you got 5 problems using this concept of works. You got the spring, basically the spring and the rope and the bucket are the two that we're doing. I don't think. Oh, yeah, skip number 6. We're not gonna do that. So guys, that's like 4 problems. There you go. Okay, so, like I said, but again, the reason I do that is because I wanted you to keep working in those packets too, at the same time with that. So skip 6, so just 1, 5, 7, and 12. I think it's, yeah, just 1, 5, 7, and 12.
We still have one more lesson in this chapter.
Yeah, Monday.
So.
Tuesday? Yeah, I think so.
Okay.
I think so. Let me.
I just think that'd be a better alternative than waiting a week.
Yeah, I've got a kind of a review sheet just on reviewing area and volumes. We've been kind of doing that. That I could give you. I could give to you today.
Get it very, very good time.
Yeah, I can print it, and you could get that today if you wanted to work on it. So you didn't have as much to do Monday night.
Yeah.
Then you could just do the new thing. Because we'll do that on Monday. Tuesdays is gonna be kind of answer questions. I got a worksheet. Yeah. Just whatever. And so yeah, I think so. I think that's a good idea.
Sounds good.
And then you'll be gone the rest of the week.
Yeah, gone the rest of the week and then the first half of the next. Well, through Wednesday, but then we have one north Thursday. So we'll be gone for like.
Right. Yeah, and somewhere in there, we'll probably start to find some really what you're missing. That's kind of work days, review days, just, I mean, I'll probably have recordings.
Yeah, no, I'll watch the videos.
But it'll be a lot of work time too. And then, just kind of getting ready for different finals. Usually I give the very first one about a week.
Okay.
So we may have to take it out during Bearcat time.
Yeah, well, and I have to go.
And roll it for
Can the spring test be negative?
no, it should not be negative. So X, yeah. So on the spring constant, so if you compress it or stretch it, doesn't matter. So if you compress it 2 feet, that's a 2. If you stretch it 2 feet, that's also a 2, right? I mean, it's just the distance you go that is your X.